A spanning tree of a graph with n nodes is a subset of the edges that connects all n nodes together without forming any cycles, and uses exactly n-1 edges. Prerequisites: union find for Kruskal, we use it to check same versus different component when adding edges. Min heap for Prim, we use it to pick the cheapest crossing edge. See the union find and heap tutorials for details. In the real world, network design uses it to connect offices or cities with minimum cable or road cost. Ethernet switches use a spanning tree, the spanning tree protocol, to avoid broadcast loops while keeping every node reachable. Infrastructure like power grids and pipelines also use spanning tree ideas to connect all points with minimum length or cost. A spanning tree is n-1 edges so the graph stays connected and there are no cycles. We need exactly n-1 because one edge connects two nodes, and each new edge adds one more node without a cycle, more would create a cycle. To build one, generically, add edges one by one. Add an edge only if it connects two different components. Use union find, if the two endpoints are in the same component, skip, if not, add the edge and merge. Stop when we have n-1 edges. Two common algorithms for minimum spanning tree are Kruskal, sort edges by weight and add in order as long as no cycle, and Prim, start from one vertex and repeatedly add the cheapest edge from the tree to the rest. Technically, we pick a subset T of edges of size n-1 so the graph on those edges is connected and acyclic, that's a tree. Kruskal, sort the edges, for example by weight. Initialize union find. For each edge, if the endpoints are in different components, add the edge and union them. Stop at n-1 edges. The cycle test is, adding an edge creates a cycle if and only if the two endpoints are already in the same component. Prim, start from one vertex and repeatedly add the minimum weight edge from the tree to the rest, for example using a heap. Stop at n-1 edges. Both algorithms produce a minimum spanning tree. We'll process edges one by one, add if they connect different components, skip if they would form a cycle. Union find tracks the components. Edge 01, different components, so we add it. Edge 12, different components, add. Edge 23, different components, add. Edge 03, 0 and 3 are already in the same component, so we skip to avoid a cycle. Edge 34, different components, add. We now have 4 edges, n-1, so the tree is complete. We have n-1 edges, so the spanning tree is complete. We stop here and don't process the remaining edges, they would all connect nodes already in the same component. We'll build a minimum spanning tree with Kruskal's algorithm. Edges are sorted by weight, we process them one by one, add if they connect different components, skip if they would form a cycle. Union find tracks the components. Edge 12 weight 1, different components, so we add it. Edge 01 weight 2, different components, add. Edge 23 weight 3, different components, add. Edge 0, 3, weight 4, 0 and 3 are already in the same component, so we skip to avoid a cycle. Edge 3, 4, weight 5, different components, add. We now have 4 edges, n-1, so the minimum spanning tree is complete. We have n-1 edges, so the spanning tree is complete. We stop here and don't process the remaining edges, they would all connect nodes already in the same component. Prim's algorithm also builds a minimum spanning tree. We start from one vertex and grow a single tree, keeping a min heap of crossing edges from a vertex in the tree to a vertex outside. At each step we take the cheapest such edge and add it. Here we start at node 0. The cheapest edge from the tree to the outside is 0, 1 with weight 2. We add it. Now the cheapest from the tree to the outside is 1, 2 with weight 1. Add it. Cheapest is 2, 3 with weight 3. Add it. The heap root is 0, 3, but vertex 3 is already in the tree so we skip it. We take the next minimum, 3, 4 with weight 5, and add it. We now have n-1 edges, minimum spanning tree complete. V is the number of vertices, E the number of edges. Kruskal, we sort the edges in O of E log E, then process each with union find in almost constant time. The sort dominates, so time is O of E log E. Prim with a binary min heap, we consider each edge once and do O of log V work per heap operation, so time is O of E log V. Space for both is O of V plus E, the graph itself, plus O of V for union find in Kruskal or for the heap and keys in Prim. Kruskal, sort the edges by weight, initialize union find. For each edge in order, if the endpoints are in different components we add the edge and merge. Stop at n-1 edges. Prim, start from one vertex. Keep a min heap of edges from the tree to the rest. Repeatedly take the cheapest such edge. If the new vertex is not yet in the tree, add the edge and the vertex, then push all edges from that vertex to the outside into the heap. Stop at n-1 edges.